A comprehensive analysis of feature-based image recognition using ORB and RANSAC algorithms. Our presentation consists of our objectives and thesis, mathematical methodologies, results analysis, and some practical usages. And now, let me start with motivation. Robust image registration is super essential in fields like medicine and autonomous systems, where alignment errors can have major consequences. This report evaluates the ORB RANSAC algorithm to balance computational efficiency with registration accuracy across diverse real-world scenarios. Oriented fast and rotated brief, which is our brief, provides an efficient and rotation invariant technique, making it a compelling subject for this performance evaluation across various transition types. Our key objectives are to evaluate ORB RANSAC's performance across different image types and geometric transformations while comparing the robustness in handling different challenges and with and without rotations. We also hope to provide practical implementation and mathematical understanding. We believe that ORB RANSAC demonstrates excellent rotation invariance and computational speed, yet it may show some limitations with complex perspective transformations. Next is a review of the literature we used. Feature-based recognition has progressed from foundational coordinate detectors like ARIS to robust invariant descriptors like SIFT and SURF. ORB was then introduced as a highly efficient alternative to them by strategically combining existing techniques. It builds upon fast algorithm for rapid key point detection and the brief descriptor for efficient matching. Then, the RANSAC algorithm revolutionized robust model fitting by efficiently estimating parameters from data outliners. Last but not least, deep learning approaches like Superpoint represents the latest advancement in image recognition. Now, I will pass it to Jack to talk about the methodology and mathematical foundations.
Yes, fantastic. Now, I shall talk about the methodology and the mathematics behind the whole algorithm. So, here is the pipeline of our whole algorithm, which I will dive deep into this pipeline. So, we'll start with a robust image loading and processing. And a key part of our method is to stimulate the real-level conditions through the controller geometric transformations like rotations. And this allowed us to test the unknown and accurate data sets, so we will obtain the algorithm's accuracy. Next is our ORB, or feature detection. Our ORB can detect up to 5,000 features, and this number is chosen to empirically strike a balance between the accuracy and the computational speed. That is the feature matching. And once we have our features found by ORB feature detection, we will need to match between these two images. And we will use Hamming distance, which is optimal for ORB's binary detectors, and keep only the top 90% of them. And we'll set a clear set of points for next stage. Next is our also major algorithms, which is called RANSAC. And this is like this can provide a very brilliant method to remove outliers, so our algorithm can run more accurate. And this is like the classification for our quality, so we can determine whether it's good or not. So now, let me dive into the mathematical models. First, we have this optimization framework, so we can find the difference between our reference image and the transformed image outputs. And second, is this pre-processing. So we use geometric transformations like rotation to find a standard transformation model using a rotational matrix as shown here. So this is the evaluation. So we know that if our algorithm perform well, And this is the formula for our handling distance calculations. And this is our computational complexity. And we can see that one major advantage of ORB ransack is that it has a high computational speed. Like if you see at the top left corner, the feature detection complexity is linear at O of n. So it runs very quick. Yeah. Next, I will pass the time to Isaac to talk about the experimental results.
Okay, so thank you, Jack, for explaining the mathematical principles behind our project. So now I will mainly explain some of the implementations of the image registration. Okay, so in this session, I'll first walk through the simple image and complex image experiments, show some detailed per case visualizations, compare performance by transformation type, and finish with practical insights and limitations. So this slide summarizes some registration results for simple planar book image across 4 test cases, which are namely, firstly, vertical tilt, secondly, 5-degree rotation, thirdly, 10-degree rotation, and finally, a mixed transform. So note that rotation-only cases achieve an excellent overall accuracy, with here roughly 80%. And on the lower half, you can see some processing metrics, which include matches, runtime, SSIM, and NCC. So for planar and low texture scene, ORB ransack gives a very good result under pure rotation, but it's only fair under some perspective changes. So you see 24 and 25%. Okay, so here is how we really implement the project. Here is a very clear visualization. So these two are cases 1.1 and 1.2, which are a vertical tilt and a 5-degree rotation. So on the left, the vertical tilt shows fewer reliable matches. So the overall classification is only fair. And on the other hand, the 5-degree rotation shows dense and correct key point matches, and there is a high SSIM, and so this is very good. So next is the 10-degree rotation case and the mixed transform case. So for the 10-degree rotation case, it is actually as good as the 5 degrees case. However, for the mixed transform case, perspective components are included, which actually degrades the whole experimental results dramatically. Many descriptors no longer match with each other, and his histograms shift to larger Hamming distances, and overall quality has dropped quite a lot. It dropped from 79% to only 54%. And so now we switch to a more complex image analysis. So basically a person or 3D image with comparatively more rich textures and non-planar geometry. So the top table shows features, inlier ratios, match quality, and overall accuracy for 4 transformations. So the pattern is quite similar, but more pronounced. Rotation cases still perform quite good, but in this case, perspective cases actually perform quite bad. So we used this anime for an example. So visual panels for complex images. So case 2.1 and case 2.2. On the left is 2.1 is the vertical tilt. So as you can see, there is a heavy appearance change and occlusion. So many matches actually come from the stable background areas rather than from the subject. So leading to some, I'd say, incorrect alignment and low overall accuracy. So on the contrary, the test case 2.2, which is a 5-degree rotation, produces a robust matching and high SSIM. So in short, actually, rotations preserve local patch structure, quite good, but perspective and occlusions do break it. So these are the 10-degree rotation case and the mixed transform case. So it's actually quite similar to what we're talking about just now. So basically, the rotation case could vary quite well did the registration work quite well. So there is a 77% accuracy, while for the mixed transform, it is slower and it has a lower accuracy. So next is some. Okay. So next is some discussion. Okay. So I would now try to summarize our takeaways and some limitations of projects. So firstly, on the left is some positive things, including rotation invariance, a drop in perspective patterns, and perspective sensitivity, and high inlier ratios. And while the algorithm kind of struggles with some perspective distortions, and especially when the subject is non-planar, so when it's 3D, it performs exceptionally worse. Yeah. And okay, so this slide breaks the algorithm behavior into two sides. So on the left is some perspective transformation challenges, which include some occlusion and emergence, background bias. So like the image is not based on the subject and based on more about the background instead. And on the right are some rotation strings, which includes that rotation can actually preserve the key features very visible unless it is a 3D. Okay, and this slide talks about some math thing. So computational complexity. So ORV detection is effectively linear in image size, and matching with Hamming distance is simple yet efficient in practice. So the red set complexity is manageable with adaptive stopping. Okay, and I'll give some final insights to close the session. First, the feature quality beats quantity. Complex images hit the feature cap, but still perform way worse under perspective. So distinctiveness matters more than perspective. Secondly, mixed transforms behave like perspective-only cases. Perspective dominates registration difficulty. Third, computationally, the pipeline is stable and predictable, which is good for real-time users. And finally, Hamming distance is a reliable predictive metric, with its use lying in stopping, filtering, or adaptive pipeline selection. Okay, so I think this concludes the exploration resources section, and I'll pass the time to Taylor. Thanks.
Okay, so now we know what the image registration is. You just twist an image to be another one. So what do we use with it, right? The first example is the scan documents. When you scan a document, you take out a phone, you take a photo from a very weird angle. Yes, when you select the four corners of the paper, it gets warped back into a planar view, a very clear planar view. So how do they do it? Image registration. And the next part is actually scanning of moving images. When we have some in factories, right? We have moving parts of machines. They're gonna be moving around. How do we scan them and check if they work? You warp them to the same place, compare it, and then you check it. So that's basically how it works. And then you can stitch images together. When you have two images, you can actually find what parts that are equal and then just match them together. That's basically how maps works, how the satellite images get stitched together, as well as how we actually open up our camera out with a panorama view. That's basically how it works as well. But on top of that, we can also use stabilization. It's basically very similar to stitching images. We also have 3D models and aligning some medical images for extreme comparison. Basically, very similar things as well. But some limitations is that, as Isaac just said, it's perspective rotation. Right? We can use SIFT or SURF in order to improve this part because it uses AI learning. Basically, what it does is it learns from its past mistake and focuses more on perspective change, and that's how we can do it better. Or we can actually choose to even shorten the processing time. Reducing the max amount of matching points can allow a faster processing time, and even though the image registration time may be less, it will be less, and they can provide more real-time performance. So that's pretty much it. Thank you very much.
Sorry, I still have to give give some acknowledgements to Dr. Hugo Mack, our mentor, and also Dr. Jeff Wong for coordinating the whole program. And thank you for your dedication.
Thank you for the presentation. It is now the Q&A time.
So very nice work. So I have a few questions. For the first questions, so I see that you have shown quite a lot of like test cases, and in particular, you show some kind of like attractive like point distributions and so on, those kind of green circles. So it seems that all those kind of green circles are kind of concentrated in one region. So is there any explanation of like why is that the case?
Yeah, because of course, when we scan an image, we scan the entirety of the image. We don't just scan part of it. That's the point of it, right? We scan the entire image, but we just show every single point that it matches because, well, as Jack has said, we have 5,000 maximum matching points. Right? We can't show all 5,000 of them right there, right? The entire thing would just be green. So we just picked the first 100 circles that they can find, like the first 100 matching points that they can find. We just circle out to showcase how basically our model works. We scan from top to bottom, find the matching points, and try to fit the matching points together. And try to get the distance. As you can see from the bottom left graph, right? We try to fit it into a red line, and it should be good. It should be all there. That's basically how the distribution works. Thank you.
So thanks for the explanation. So that means you have actually much more than that, right?
Yeah.
And so then, like you are taking the, let's say, first 500 points or so on.
Yeah, we're taking the first 100 points. Yeah, but on average, we still have over 1,000 points per images. And also, if you notice, we actually have the image. We actually also have the image size less than 1,000 times 1,000, so there can be that many matching points as well. So we counted all 5,000 of them, but we still have over 1,000, which is pretty good for such a small size. And also, image registration isn't really used for some really large modifications, but rather pretty close points and stitching them together. Like as we have mentioned, some moving parts, right? Image here. They should be at similar time frames so that when we compare it, we know exactly when some things is going on, and etc.
So my other question is, so I see that you have some kind of quality classification based on some kind of scores, and like about 80, you say that it's excellent and very good and so on. So like, is there any reason why you do this kind of like classification? Is there any like distributions behind so on based on your that you based on?
Okay, so if you just look at the score, you might think it's bad, you might think it's good. It's not really very parameter, but language is something that we use every day. And I believe it's more layman, I guess. It's more clear to what's general public, like on how to define what's actually good in our model. We believe that over 80% is already pretty decent. Maybe some people might think, oh, 90% is 80, no, not. But in our example, we believe that over 80% is already very decent towards our model. So yeah,
it's
basically what we're
it's kind of based on like some like before we did the testing, we like look at the results, and we believe that when we look at the results, we feel like over 80 seems like a good label for it to be excellent, but like when it's like 50, 60 is like not really as accurate as you can see from it's like only it's not really that linear, it's really fair, so that's how we kind of determine the whole matrix.
So my last question is, so I see that you have tried a lot of like rotations. Have you also tried some other nonlinear transformations? So like if you have some kind of like images, you apply some kind of like nonlinear transformations. And
like 3D scans.
Yeah, maybe you have some kind of like more like highly distorted like snapshots and so on, and then you want to do the registration between them, rather than just having a kind of rotation.
I believe that's actually rather difficult considering the amount of time that we have on some of that. Most registration again is just used for some slight changes, and even if highly distorted images, they're mainly used in something like VAR in football, right? Where we can scan the pitch in various angles, and then by the camera angles and perspective, we can estimate the 3D model of the players to know whether there's like an offside or a goal or whatever. And these are some pretty complex things that we might be doing in the future, but so far, in the given the amount of time and the power that we have, the computation power, we don't believe that we can be doing this for now. So sorry. Thank you.
Can you show the picture? Oh, no. Like this works. So So when at your test cases, in this sense, one time I want to be sure. When you say this is very good, of course, then you look at the the upper top one, they are better. But then what happened to the left middle one? All your poor cases, actually the left middle one is the clearest one.
Left middle one. And that's a heat map for you. So what a heat map does, it puts the target image and our registered image overlapping them, and we generate this image by their difference in like their colors and not really colors, they really use grayscale, sorry. Like their location and like if the line features matches, and then we just define how off they are. So let's say it's right here, right? The accuracy isn't that good. It's like well, it's 49%. It's poor. So as you can see, the heat map is not looking happy. It's completely right. That's why it's poor. But here, it's very good, right? So it nearly matches together. The difference is nearly zero. If you look at a slight bar on the right, if you can see, the low is zero and it's completely black, and on top is over 100% and it's completely white. So that's basically kind of different.
So this is the difference.
Yes, exactly. Thank you.
I echo Professor Penny. So when you look at the distribution picture, the graph, the bar chart, if you compare left and the right, may I say if you have a poor the image registrations, may I say the skew will shift to left or right? If a better picture, what do you think about the distribution?
I believe some of these distribution isn't as accurate as it seems, because when we shift the perspective, sometimes the background changes with me, right? Let's say I look in front of me, I see this row only. But if I shift to the left, now I see those rows again. But when we try to register two images together, we try to register this to form some parts of the image that's completely outside, right? So that's what I'm talking about. So that's why actually Isaac talked about this, about how the background moves as you rotate the perspective. So sometimes the image registration can't really catch that. It can generate new like pixels, right? So that's why the accuracy of perspective change is as bad as it seems. But if you just compare it by eye, it's not really that bad. Even though the heat map says otherwise, but I disagree. Just look at the edges. It's completely right, but there's nothing for it to register. That's why it's like that.
Thank you.
Okay, thank you.
Thank you to the judges and group supper. Please return to your seats.